Hey guys, it's Teacher Dad. So today we're going to do a little physics experiment here, and we'll see how this works. You know how sometimes physics equations work or don't work, and you have to make some modifications. So working with some limited resources here, so we'll see what we can do. So today what we're going to be demonstrating is centrifugal force as it's applied in a circular motion, and we'll go through some of the more details about what's happening here. And so I have a video that I did similarly where you saw how you could use kind of like the dumb waiter kind of device and spin something around, and the centrifugal force and the centripetal forces that canceled each other out. And so today we're going to be demonstrating another aspect about this. So you can see what we have here is we have about 2 meters of string. On one end of the string, we have a rubber stopper that's tied on here, and I don't have a really precise scales, but this is approximately 50 grams, and so this is tied on here. Then it's passing through a tube, and this has been smoothed here on the top so that it tries to minimize the friction. I didn't have what the lab recommended, which was like a glass fired thing, so it would completely minimize the friction. So that may be some factor there that would calculate in if there's some discrepancy. And then on the other end, I have some weight attached here. So then on the other end here, I just have attached a tape measure, and this is about 200 grams. And so this is going to be hanging through the center of the tube and down from the weight. So you want to attach and move about 1 meter of the string. So I'm going to move about 1 meter of the string here, and then hold on to that with my thumb. And then I'm going to start spinning this around. And so you'll see what happens as if you are able to keep a constant momentum of the string spinning around, then you'll see that the tape measure will not go down or up. And if you start spinning it faster, then it will pull the tape measure up towards the tube. If you start going slower, then it will move the tape measure, and the tape measure would sink back down. And so we're going to get to a point where it's in equilibrium, and then I'll attempt to keep that at a steady rate, and then we need to count 50 revolutions, and then I'll just look into my video editor later on to calculate the actual times, and I'll demonstrate the times, because we need to count how long it takes to complete 50 revolutions, keeping that at a constant momentum. And then we'll be able to measure the string and be able to see the radius that it was taking in order to keep that tape measure at that distance. So we'll give this a try here. This is my first attempt at doing this, and so we'll see what happens here. All right, so you can see that this is spinning around. If I start to spin it faster, all right, you'll see the tape measure rise. If I start to spin it slower, you should see the tape measure begin to fall. Now I've got too much string out. So you have to have it at about 1 meter. And so you'll see here, if you start to slow down, then the string should go back down. If you start speeding it up, then you should see that it reaches equilibrium here. All right, so we'll start counting, and then we'll see the length of time that it takes here. All right, now we'll catch the string at that point, and then we'll measure the distance that the radius was taking to spin along that line. And conveniently here, I have a tape measure. So if I can keep the string from moving and stretch out this tape measure, I should be able to get an equivalent here of where our string was at. And we need to go to the middle of the stopper here. All right, so we're right at 15, let's see, 4 foot 9 inches, and otherwise that would be, so that 100, so that would be 100 centimeters, so 1,500 centimeters. 1,500 centimeters and 4 foot 9 inches. So we'll try that one more time, and we'll give it another, we'll give it 2 more trials just to see if we come out with a similar amount of distance there. Hey guys, so now we're ready to do the actual calculation part. And so as I did the lab yesterday, I was doing the demonstration, and the numbers will be slightly different because we'll be using the material from the book here, but I wanted to demonstrate how the lab was actually done, and then we'll be talking about how we actually calculate the values here. So first of all, you'll see on your screen there that we're going to be calculating the values from table 10.1. So we look at the mass of the stopper. The mass of the stopper was 32.6 grams, and so we convert that to kilograms, so we get 0.0326 kilograms. Same thing for both tests. Then the mass of the hanging mass there, and that's in kilograms as well. The first test was done with 200 grams. The second was done with 300 grams. So then you'll see the radius for each of the tests. So 535 centimeters, 578 centimeters, 562 centimeters. We convert those over to meters. Then the number of revolutions as well as the time. All right, so first step is we're going to be calculating, you can follow along there, but first step is we're going to be calculating the stopper's linear velocity. Okay, so linear velocity, as you'll see on the screen here, this is a calculation of distance divided by time. So in order to calculate the distance, the stopper was moving in a circular motion, and so we're going to have to use the formula 2 pi r. And so since our radius was 0.535 meters, that gives us a distance of 3.36 meters. Then our time, we had a total of 27.17 seconds. However, that was 50 revolutions. And so we want to find out how long did it take for one of those revolutions. So we take the 27.17, we divide it by 50 revolutions, we find out it was 0.54 seconds per revolution. So the velocity then would be calculated by 3.36 meters divided by 0.54 seconds, and that gives us a linear velocity of 6.22 meters squared. 6.22 meters over seconds. So next we're going to calculate the centripetal acceleration. Okay, centripetal acceleration is the formula A sub c equal to the velocity squared divided by the radius. So you can see there we have our velocity, which was 6.22 meters per second, and we're going to square that, and then that's going to be divided by 0.535 meters, which is our radius. That'll give us a centripetal acceleration of 72.34 meters per second squared. All right, and remember when you're doing that, meters and seconds get squared, so you end up with canceling everything out. You end up with meters over seconds squared because one of the meters cancels out. All right, third step then is you're going to calculate the centripetal force. So centripetal force is calculated by mass times acceleration. So the mass of the stopper was 0.0326 kilograms, or 32.6 grams, and we multiply that times the acceleration that we just calculated, which is 71.6 meters squared. And then you see that we have 2.33 newtons calculated as our centripetal force. One more step here. We need to calculate our theoretical centripetal force. So the theoretical centripetal force is determined that when the stopper is at a constant speed, the magnitude of the weight of the mass of the stopper and the tension acting upon the stopper should be equal. So the weight of the hanging mass is equal to the theoretical centripetal force. And to calculate that, we take the weight of the mass, which was 200 grams, and we multiply that times our gravitational acceleration, which is 9.81 meters per second squared. And we see that our theoretical centripetal force should be 0.196 newtons. Now, we need to compare that to the actual reading, or the actual measured centripetal force that we got. So we have to calculate our percent discrepancy. In order to calculate that, we need to say the theoretical centripetal force is, we subtract the calculated force, and then you want to take the absolute value of that in the event that it is negative, and divide it by the theoretical value, and then multiply by 100. So we had 1.96 as our newtons as our theoretical force, minus 2.33 newtons gives us a negative 0.37. We take the absolute value of that and divide it by 1.96, gives us a 0.1887755. We multiply that times 100. We get our percentage of discrepancy, which is 18.9%. All right, so that works through the first one there in your table 10.2 that you should be working on. And so you need to take the values from table 10.1 and finish filling out the rest of the values for table 10.2, and then you can go on to the web page and you can submit your answers for our lab today. So hopefully this worked out well for you, and if you have any questions, you can contact me. But again, thanks for watching, and hope this was enjoyable and something interesting for you, and we'll see you again on the next one.